Hello. Hi, Simon. Hello, everyone. Thank you so much for joining us. Today is the second and final day of this Fonts and AI conference. We are very excited. I was just telling Simon that when I was talking to the program committee and saying like, let's do this Fonts and AI, everyone was like, okay, get Simon. So we're very happy that we have Simon Cozens with us on the program today. I am going to steal 2 minutes of the presentation time, which you can have later. It will be my fault I delayed. But I thought it would be really nice to share something very special with you. I don't know if John is watching this already. I hope he is, but if not, I send him to watch the recording later. I'm going to share the screen of this. So this is written without AI and completely by a human who is John Boardley, completely unrelated to this conference, except that he is the other, main person at ILT. And he has written this book. John, if you don't know him, is the person who launched I Love Typography in the blog format in 2007. He's an author, writer, designer, mainly an author, and he's written previously other books with the Bodleian Library in Oxford. And now there is this new book which he has received today in print. I think the launch is today or in 1 week. I don't know, but you can pre-order. So if you would like to show some love and appreciation for ILT and for John for all the amazing work he does, please go buy his book. It's amazing. And it looks gorgeous as well. I mean, this is spectacular. And this is one of the places where you can get it. It's not a cheap book, but it's worth every ounce of it. So you can get it from the Bodleian Library. You can get it from Amazon and other places. It's first in the UK and then it will go to the US. But please show some love to John and get his book. And that's it. So that's all. I leave you in the very capable hands of Simon. Simon, I will go back now to the backstage. I will come back when you are ready to take questions. Okay? And thank you so much. Thank you for all the audience.
Thank you very much. Right, I will just start my presentation, I hope. Yes, okay, so thank you everyone. My name's Simon Cozens. I'm going to be talking about two things today. The first part we'll be talking about machine learning, and the second part we'll move on to talking about fonts. But just a couple of things before I start. First thing I want to do is just to start running this program over here, which we will get onto later. Okay. And the second thing I want to do is just to make it clear, I'm a fonts linguistic programming consultant with a company called Cozens Software. We've got a number of clients that I consult for, but I want to make it clear that the clients may not agree with some of the sentiments in this presentation, or they might agree, but they may not be able to do so in public. Anyway, please remember, I'm speaking in my personal capacity today as somebody who basically messes around with machine learning and fonts. I don't really enjoy consulting on fonts and AI. One of the reasons for that is that, as we'll see later, this stuff is kind of hard, it's unpredictable, and it would terrify me to be on the hook for delivering a working machine learning project. So it's just a hobby. And I'm going to be duplicating a little bit of what Dirk said yesterday, but I think that's okay. This is a complex topic, and it's probably good to hear it more than once in different ways from different people. So you'll already have seen that I'm making a distinction here between machine learning, ML, and artificial intelligence, AI. And to understand what that distinction is, we need to go back in history a little bit. In 1950, this guy, Alan Turing, wrote a paper called Computing Machinery and Intelligence. And he proposed a number of ways that we could train a thinking machine. And he came up with two main strategies. The first way was about teaching it how to reason. So you teach it a large number of rules and facts and logic about the universe and how things work, and then teach it to reason. And then the second way was what we now call machine learning. It's more like copying the way that the human brain learns. And the story of artificial intelligence, the story of AI since the 1950s, kind of follows those two approaches that he proposed. So in the 1960s and 1970s, people were trying this kind of logic, rule-based approach, particularly coming out of MIT, Stanford University. They're writing code in Prolog, programming logic, and Lisp. And they would build these kind of huge towers of logic and information. There was one project called SICK, which went on for many, many years, and they kind of hand encoded like 25 million statements about the universe. Grass is green, you know, all of this kind of stuff. Put it into a massive database and kind of hoped that reasoning would happen as a result of it. None of those logic-based approaches really got off the ground. There was one famous one called Schlurdu, which linotype fans might appreciate, which was this kind of block universe. And you could interact in natural language. You could say, pick up a big red block, and it would do that. You know, grab the pyramid. Well, I don't know which pyramid you mean. Schlurdu was actually a rigged demo. If you followed the script, it would give you the right results. But if you asked it any questions that weren't in the demo, it actually wouldn't understand. And a lot of these logic-based approaches didn't really work. Meanwhile, kind of slowly, quietly, in a kind of parallel track, there was a man called Frank Rosenblatt, and he was working on the other Turing proposal, the biological model. Let's build something that looks like and works like a brain. So how does the brain work? The fundamental unit of processing in the brain is the neuron. Here's one. You've got these spiky bits on the left here, which receive electrical signals, whether it's from nerve cells, whether it's from other neurons that they're connected to, other bits of the brain. They receive these electrical signals. There's this big round processor in the middle that decides what to do with those signals. It combines those inputs, and based on their combination, either it fires another signal out, down the other spiky bit, down the tail, or it doesn't fire it. Now, in a way, that's just an electrical circuit. And what Frank Rosenblatt realized was that you could actually build these things in hardware out of electrical components and wire them together like a brain. The only problem with this is that there are 86 billion neurons in the brain. Wiring that together is going to be tricky, especially in the 1960s. But at the same time, you can also see this as like a mathematical function. It takes a bunch of numbers as inputs, these x's on the left, and based on different combinations of them, the different weights attached to each of them, we sum those and then we decide what we're going to do with the output. It's a mathematical function. So you can model that not just in hardware, but you can also model it in software. And this is called an artificial neuron, also known as an artificial perceptron. What can we do with it? Well, by having it play with these individual weights on the left, you can train it, you can teach it how to do things. And this is a machine that can learn. So for example, let's say we want to train this perceptron here how to run a coffee shop. We have a shop and it sells coffee and donuts, but we're not going to tell it how much the coffee is, and we're not going to tell it how much the donuts are. We're going to have a customer come along, and it starts out in a completely random state. It's got no idea. Customer comes along and says, I want to buy 4 coffees and 2 donuts. And the perceptron adds together the weights, does the multiplication, does the addition, and says, that's going to be $560, please. It's the coffee shop at 8 High Price Sharjah. And we say, no, it's not. It's going to be $21. Because we know, behind the scenes, we know that a coffee is $4 and a donut is $2.50. So the true thing that it should have predicted is $21. The amount it did predict, the predicted value was $560, and we can work out how wrong it was. Take the difference, square it, and that's called the loss, how wrong the neuron was. And then there's a bit of mathematical magic we can do called backpropagation. And what you can do with that is you can take that loss and send it back through the neuron and adjust the weights so that it will be closer next time. So the next time, there we go, we're backpropagating the loss through the weights. Next customer comes along and says, I would like 3 coffees and 1 donut, please. It's got different weights this time and says, that'll be £7.96. And we say, no, it won't be. It'll be $14.50. And then we can work out the loss, send it back through the neuron, adjust the weights again. And eventually a customer will come along and say, I'd like 5 coffees and 2 donuts. And the machine will say, that'll be $25. And we'll say, yes, it is. That'll be $25. We've fallen to zero. The weights are correct. We've learned the right prices for the coffee shop without us telling it what those prices were. So what we've shown here is that one single perceptron like this can learn the correct weights for the function just by multiplying numbers, adding numbers together. It can work something out by itself just by seeing examples and trying them out and being told how wrong it was. And it turns out that we can prove mathematically, if you wire enough of these perceptrons together into a big network so that they're all passing information from one to another like a brain does, you can actually model any mathematical function. So anything you can express as a mathematical function, you can train as a model. And the best bit is it doesn't matter whether you know what the function is or not. It doesn't matter if you know how to express it. Just by trying out these combinations of weights, you can eventually learn to associate the inputs that you've got with the outputs that you want. Now, we knew that in theory back in the 1960s, 1970s, but nobody could actually get it working in practice. Because the problem is that as information goes through these layers and layers and layers of perceptrons, the signal that you get back at the end, when you're trying to send that loss back through the network, gets smaller and smaller and smaller. We say that the gradients vanish. And so functionally, we could only get through about 3 or 4 layers before the signal vanished away to nothing, and you couldn't train anything anymore. And then in 2015, these guys, Joshua Bengio, Jeffrey Hinton, Jan LeCun, doing their Kraftwerk impression at the top, published this paper, Deep Learning. And that summarized a number of tricks that people had learned at this stage about how to avoid those gradients from vanishing. Part of it was due to having better hardware, using GPUs. Part of it was arranging the layers in certain ways. And then there were various mathematical tricks that would make the back propagation work better. And it worked. It worked really well. Our machines were finally learning. We had AlphaGo, AlphaZero. We had better computer image models and vision models and so on. So let's summarize what we mean when we're talking about machine learning. We've got a network of perceptrons arranged in certain ways in certain specialized architecture. They've been trained to solve a specific problem. It's done very quickly, very easily, with generally very high confidence and very high accuracy. And it's been trained on tasks, frankly, that benefit humanity. Well, what do I mean by that? At the start of this talk, I started a program up here. And is it finished? It's still going. It's nearly finished. And what this program is doing is it's looking at images of MRI scans of the brain. And some of these images have got tumors and some of them don't. We've shown it this specific task. It was trained very quickly and easily. We're going to ask it basically whether an image has got a tumor or not. The code representing the training model is just that. It's very simple. And again, in the, 15 minutes it's taken me, it's pretty much finished training, and it's reached an accuracy of 95%. This is running on my home computer here, which today is solar powered, and we have run this model up to 95% accuracy. You can probably see it. There we go. And then we can show it another image, and it can say, this image has got no tumor, confidence 99%. Brilliant. So that is machine learning. Let's go back to our slides. But it's not intelligent. So again, late 2010s, early 2020s, people started thinking, what if we marry these two approaches to thinking machines? We take this whole project of like summing up the whole of human knowledge. And we encode that as a stream of numbers. And we train a massive, massive network. And then we can ask it questions. We can turn our questions into a stream of numbers and say, give me the most likely stream of words that forms the answer. And that's what we're talking about when we talk about large language models. They're models like machine learning models. They model language and they are massive. These are things like Gemini, ChatGPT, Bard. They're still not intelligent. They're very good at word prediction. They can produce text that looks like it was written by a human, but they don't understand what they're writing. So there's a distinction here between machine learning, artificial intelligence. You've still got a big network of perceptrons. It's being trained to solve the problem of language and speech and continuing sentences. It takes a lot longer. It may not make mistakes, and it drives vulnerable people to suicide. But it's still not intelligent. They're not doing any thinking. But the counter argument to that is, no problem, say the AI companies will just show these models lots of examples of what people sound like when they're thinking, when they're reasoning things out, and we'll ask the model to generate some text that sounds like it's thinking. And although I've called this a bag of crap at the start of this talk, it also kind of works. You've got something that sounds like it's thinking. And one of the original arguments in Alan Turing's paper was that if you can't tell the difference between a machine that sounds like it's thinking and a person that sounds like they're thinking, then functionally there is no difference. You've kind of got artificial intelligence. What is the difference between something that sounds like it's thinking and something that is actually thinking? And does it matter? In the first era of AI, in the 60s and the 70s, with those Lisp hackers, we had a rich philosophical literature about these topics. You had people like Marv Minsky, Douglas Hofstadter, Roger Penrose writing about things like what is consciousness, what is intelligence, is there a difference between real and simulated consciousness? What I find strange is that in the 2020s era of AI, we're not seeing the same level of philosophical investigation at all. And I think that's probably because the first era of AI was driven by university professors, publicly funded researchers who were trying to build a project to make the world better. And the second era of AI is driven by tech dude bros trying to build a product to sell. And so what you will find is that any concerns you have about AI, whether they're philosophical, environmental, societal, mental health concerns, will often be dismissed immediately as you being deceleration, getting in the way of progress, when what they actually mean is you're getting in the way of them making money. And if you think I'm overstating the case, we've got Nick Clegg here from Meta saying that he, a former UK Deputy Prime Minister, this guy, saying that artists and designers will just have to accept plagiarism because the AI business model wouldn't work without it. Right, rant over. Let's talk about fonts. The point I'm making is that it should be machine learning rather than artificial intelligence that we should be looking for things that can help us with font production. And that means we're going to have to be training new machine learning models. Let's say you're a foundry and you've got a library of fonts that you maintain. A new currency sign gets added to Unicode. Maybe it's the Saudi Riyal, the UAE dirham, and maybe not all of your fonts have things like the Indian rupee yet. Wouldn't it be nice if, based on the style of all of the other letters in your font, we could automatically draw those which are missing? Or let's say you're a CJK foundry and you really don't want to draw 50,000 Chinese characters by hand. You just want to draw enough glyphs to establish the style and then push a button to create the rest. That sounds like the sort of specialized job that a machine learning program would be very good at. I started thinking about this late last year. I tried to create a model myself and I didn't get very far. I started looking around at the state of the art. You'll notice that all of these papers come out of Peking University in China. I don't think that's a coincidence. But I wasn't too happy about using these either. And I parked the idea for a while. And then in May this year, Aaron Bell messaged me and he said, if you were going to work on this program, how would you approach it? And I sat down and I wrote a long response to him. And then I realized, actually, that kind of sounds like a plan. So here's the plan. These machine learning models are very, very good at raster images. Okay, they can consume them, they can generate them, because a raster image is to a computer just a big matrix of numbers. And that's what these machine learning models are made out of. They are relatively poor at generating vector sequences, which is why these guys have been trying these various papers. They started generating vectors, but in the end, their latest models have switched to generating like big raster images of glyphs and then trying to auto trace them. And it's worth mentioning them that none of these ML researchers are font designers, or from what I can tell, I don't think they're really working with font designers and engineers. So they're not actually thinking about the kind of things that font people think about. They're using quadratic curves, they're not using cubics. They don't think about what a well-drawn glyph should look like in terms of point placement. They don't think about master compatibility and variable fonts and that sort of thing. They're doing their stuff in a very computer sciencey sort of way. So here's what we're going to do. We will do a fairly standard image-to-image style transfer. This is a sort of solved problem in machine learning. You've probably seen, like, draw this in the style of Picasso. So we can take our font, we can reduce it to a style image, create what's called an embedding for that sort of represents the style of the font. We'll do the same for the glyph that we're trying to generate. We'll put them together, and that will hopefully generate a stylized real sign or whatever. And then at this end on the right, we will train a submodel to do the vectorization, to do the tracing for us. This is a kind of discrete subtask, take an image, turn it into vectors. But we're going to train it to do it the way that a font designer would do it. And here's the key insight. When computer science people generate vectors, they're usually generating something like SVGs. So you've got moves, you've got cubic curves, you've got quadratic curves, they've got lines. But font designers tend to think more in terms of placing nodes rather than placing segments. So where is the node and then where are the handles? We like to have handles that are either horizontally aligned, vertically aligned. We like nodes that turn into lines and lines that turn into curves and so on. So instead of doing what the computer science guys have done and sort of teaching it to emit SVG, let's develop a language that represents the kind of output that we want to see. We want to see horizontally aligned nodes, so we make a command for that. We want to see vertically aligned nodes, so we make a command for that, and so on. And again, we work out the loss between the commands and the coordinates that the machine is generating and the ones that would happen if a designer did it. And then we train a model to minimize that loss. And I think this is super important, because if we can do vectorization in a way that type designers would do it, then we have that kind of bridge between the raster world that ML models are really good at and the vector world that we want to see as our output. So I sat down and I wrote some code to do this sort of encoding, to do this sort of middle vocabulary, turning a glyph into different nodes and different positions and so on. And since I kind of knew exactly what I wanted for the ML part, I just on a whim, I fired up Gemini and said, you write this bit, give me these classes, give me these models, give me this network. And although I'm sort of naturally as an AI skeptic, as you might have gathered, it's been a really interesting collaboration. It initially felt a bit like an architect. You're working with a builder. I knew what I wanted to see, and I could give it very precise instructions about how I wanted the code to look. I just couldn't be bothered to write the code myself. But after a while, I got stuck. It wasn't learning correctly, and I wasn't getting anywhere. So I started asking Gemini for help. And it came up with various ideas to help the training, and I threw in some ideas of my own, and I would say things like, well, I think this might help, but I'm not sure. What do you think? And it was actually really helpful. Sometimes it introduced some bugs, But as I told it the symptoms of what I was seeing and took a few debugging steps and sort of told it, it was able very quickly to work out what had gone wrong. And there have been quite a few occasions on this journey where it was able to join the dots and find a solution about a bug that would have literally taken me hours to find out. So we were able to have a conversation about, what will work, what won't work. And I could say, well, I don't understand why that would help. Could you explain it to me? And it would. But one of the reasons why I don't like working with machine learning, as I've said, is that you have this big kind of inscrutable network of perceptrons, and the path to progress is not linear. It might work, it might not. You might try something and it might help and it might not help. And it's very easy to kind of flail around if things aren't working. And Gemini was very good at sort of helping me to think systematically. Okay, start with a single glyph, scale up to a range of glyphs, and now try this. It was good. And I don't know, it's a bit of a superstition, but I kind of felt like because Gemini is a machine learning model, it was particularly good at understanding machine learning models. So I asked it about that. And it said that it's like characters in a play don't know much about literature. And that blew my mind. And for all that these large language models have a reputation for being obsequious, I would make a suggestion. It would say, no, don't do that. Don't change more than one thing at once. It's not going to work. Be systematic. And in return, I taught it proper British swearing. I said that if you're working with me, you don't need to apologize when things go wrong. Just give a culturally appropriate response. And it was able to do that. So I was very happy with that. So let's do the big reveal. Here is where I'm up to, not in terms of glyph generation. I haven't got to that bit of the problem yet, but the specific sub-problem of tracing a glyph image in a way that a type designer would do it. Let's go over here to a piece of software called TensorBoard. This is like crack for machine learning engineers. If you have any kind of obsessive tendency, you will spend all day staring at this going, is it going up? Is it going down? Is it flat? I don't know. You ought to leave it alone for a week to train, but you just can't stop yourself from fiddling with it, and you can't get any work done in the meantime. Now you can see that this is a model I've been running today. It's not got terribly far, but you can see that it is training very, very smoothly. The losses, all of these different losses are going down very nicely. It is learning the right commands. It's learning how many contours there are in each glyph, which is pretty important. It's getting the coordinates in the right place. It's getting the right number of nodes. The area of the glyph is right. The total is coming down. Excellent. Really, really good. That's how it does on data that we've shown it. And then what you do after that is you have a separate set of data and you find out how it's done on the data that you haven't shown it. See how well it generalizes. And you can see that, well, it's not doing quite so well. Some of the things are going down. The contours are good. The coordinates are really, really good. The area is going down. The total's going down, but it's not quite got the idea of the right commands at the right times. But still, things are going well. We are, 20% done? We've got 95% accuracy, which is great. So let's have a look at the actual images that it's generating. It's not encouraging, is it? The green are what we expect, and the red is the vectorized version that it has come up with. And you can see that it's not really ready for use. But personally, I'm actually quite encouraged by this. There are certain things about this that tell me I'm on the right lines. For example, let's take a look at this G. We know it's got one contour. Oh, hang on, it's just produced a new epoch. Excellent. All right, the B has got two contours. Brilliant. It knows that it's got an outline and a counter. If you look at all of these, the ink is pretty much in the right place. But obviously not ready for prime time. The concept's good, and it is learning, but it isn't generalizing. And it's a matter of fine-tuning. Maybe I need more time. Maybe I need more training. Maybe I need a bigger data set. Maybe I need to change the size of the model. I believe it's going to get there, but I don't know how it's going to get there. And this is seriously something that I've been stuck on for the past couple of months. It's a research project. I was hoping that I would have something, presentable and usable by this conference, but I haven't. And as I've said, these things are hard, and you never know whether the steps that you're taking are going to help or hinder. But I think what I've got here conceptually works. And I think I've also got a genuinely new approach, which is an approach focusing on the things that designers care about and expressing these vector glyphs in ways that designers expect. And I think if we do get it right, we can train these models which kind of correct themselves in vector space. And that's going to be really important as we look at variable fonts, where you really want the point placement to be compatible between masters. So I'm sorry I didn't get you something wonderful that you can take away. I'm still working on it. It's a research project. And I'm hoping that at the next Fonts and AI conference, I'll have some better news. Thanks very much. If there's questions, I'd be happy to try and ask them.
Thank you so much. And I think I would like that a whole course with you to just sit and pass through it, because like this is so cool. Like you're quite good. Now I understand why they were saying get Simon. So really, really cool. I have a question. Speaking of variable fonts and multiple others, how, like I have a wish list. I want something, whether it is machine learning or AI or whatever it is, to make my masters compatible without me having to do anything. Like just click a button and just, like how difficult is this?
So the problem we have with this whole artificial intelligence boom at the moment is that it obscures really how difficult some tasks are. The problem of making masters compatible is something that probably could be done with machine learning, but is much, much easier to do with standard traditional programming techniques. So it's a tool that we could write, and we could probably write it much faster, but we don't need machine learning for that sort of thing.
Okay, so that's on my wish list. Okay. So we have things in the chat. If you have questions, please put them in the Q&A. But I will read the one up in the chat. So Thierry is saying, I asked Axelian the same question yesterday, but I'd love your view too. How can we normalize paths or train an ML model to understand them when different node positions or path orders can produce exactly the same visual result? And beyond that, no, you know what? Just answer that one because there's two more sections, and you're
well, the second one about how we train them to generate good paths is exactly what I'm trying to do at the moment. And so the question of normalizing this was again something that Gemini explained to me. I thought.
Wait. What is normalize a path?
Okay, so you want to make sure. There are many different ways to trace a glyph. You know, you could start here, you could start here, you could start here. And you need to show the computer the right one. Because, you know, if it starts down here and you were expecting it to start down here, you would say that's wrong. And it wouldn't learn. So what I started with was like make the southwesterly node of each contour the first contour, and then kind of go from there. But Gemini said that's not efficient. You should try, the way to train an ML model to understand it is actually to roll the contours to start at different positions each time. And that is okay. And I'm like, how can that be? You know, when you're going to create a loss and say, but it's wrong. And what it explained to me was that you will be penalizing it for, let's say there are, you know, 4 different start positions, and you know, we expect it to start here and it starts here, but we are showing it, you know, 4 different rotations. So, you know, 3 times out of 4, it's going to get the wrong answer. But if it tries something over here, then 100% of the time it's going to get the wrong answer and it's going to be penalized for it. So if you show it this hundreds and hundreds of times, it will learn, well, I kind of get a score for getting one of these right, but I don't get a score for getting this one right. So the answer is, strangely enough, it doesn't matter and you don't need to normalize the paths. That was completely counterintuitive to me. And it was very impressive that Gemini was able to explain it in a way I could understand.
Okay, nice, nice. Okay, there is also in the follow-up from Thierry, the next challenge is even trickier. How can we teach a model to grasp the intended shape to find its center line or generate a consistent outline?
Yes, and this is again one of those questions where I don't know whether it is better to use ML or to use standard computer vision techniques, computer geometry techniques. I'm not sure which is best. I haven't tried it. This is what I'm trying to do, is to generate consistent outlines. Center lines would be an interesting problem as well. And you could probably do the same thing that I'm doing, but saying instead of generate the outlines, just generate the nodes for the center line. You could take the same model that I'm using, but just give it different input for the same raster.
Okay, that all went over my head, but I think Thierry.
Hopefully, Thierry got it.
I grasp some concepts of it. It's okay. I'm a designer. I will understand what my brain is able to do. So, anyways, it's okay. Good. We have questions. By the way, guys, John wasn't here for my intro. So he's saying great talk to Simon, not to the stuff I said. He doesn't know he's going to watch the recording. We have a question from Tom. Is the main benefit of lots of perceptrons in network the serial plus parallel calculations, or is there something else? And also, please explain serial plus parallel calculations.
Okay.
Yeah, serial one after the other, and parallel would be in parallel.
Yeah.
Happening.
So it's not about the amount of processing you do at once. It is the amount of complexity of the model that you create. So when you saw one perceptron, you saw one neuron, all that can do is multiply numbers and add them together. It is only if, when you start connecting many, many, many neurons together, that you get more and more complex functions. And so the deeper your network, the more information it can process and the more complex a relationship between the input and the output it can produce.
Okay. We also, yeah, it's so funny. Like, you speak English and I understand every word, but I don't.
Sorry.
No, it's good. It's good. No, no. Look, what I liked about your talk is that it makes the topic approachable to those of us who have no background in this. And this is why I was saying I think we need a course in this, because those of us who do not code and do not develop are going to be dramatically affected by the new technology, and we need to find a way to understand it. And like, it's so difficult. Like, you don't know where to, it's like someone puts in front of you a massive cake, and the cake will either give you diabetes or is going to make you high and happy, like it's a cake from Holland. Yeah. And then, but you don't know where to even start, because like it's this massive thing. So it's okay that I don't understand everything. I think there will be other designers or other people on the conference who are also like a little bit flustered, but totally fine. We'll get there.
But equally, I would say that these people doing the machine learning research in the universities and stuff, they also need to understand you guys.
Yeah.
Because they're trying to do this image generation, glyph generation without reference to good practices in type design.
Yeah, and I get the feeling as well that the way we approach type design can perhaps give clues as to how the process needs to happen, because we're the ones who know how to go from regular to bold to black. Like,
Exactly.
it's not just random. We know the principles and you internalize the process. And sometimes that process can give insights as well. So yeah,
So
Simon.
next time, the next conference will be industry and academia.
Yes, 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 yes. So good. There is something. Oh, we're going over time. It's okay. It's fine. Someone is saying, based on your experimentation, do you think that some existing techniques would already be more successful if there were a large amount of high quality training data?
I don't know. I mean, I'll be honest, I'm using the Google Fonts library because there's 1,000 fonts in there. With the kind of stuff that I'm doing in this talk, the vectorization, you can generate as much data as you want. Because, for example, you can put, a circle in one corner and say, trace it here. And then you could move the circle along and say, trace it here. And so you can generate, hundreds and hundreds of things just from one shape. I don't think it's the data that we're struggling with. I think it is kind of knowing what to do with it.
Okay, cool. There's something in the chat. Lawrence is saying, would there be mileage in aiming for a type 1 style sub-routinized representation? We also need to please a definition of what that means. So start position issues go away and glyph portion similarity is exploited. So first, what is subroutinized representation? And then please answer the question.
I think it's basically, I'm not 100% sure, I probably should know this, but I think it's basically components inside the font. Or bits of the curve you can use again in other places.
Okay. Yeah. Okay.
Possibly, I don't know. I mean, we're in a research stage. We can try all these things and see what works.
Cool. Okay, so Rafael is saying, hi Rafael. Simon, awesome talk. I've been experimenting briefly with finding the center line of a closed vector shape. Would you be interested in checking out what I've been working on? If
Definitely.
so,
Definitely.
yeah, I can put you guys in touch, not a problem. By the way, Toshi has a script that finds the center line of any glyph. I asked for it when I was his boss. That was one of them. Yeah, because that's how I draw the bolds. I do the regular, I find the center line, I give it, I do the thin, and then I extrapolate, I get the bold, and then I fix it. So anyways, okay, cool.
There's a lot of techniques in computer graphics world for this. If you look for, I think they call it heart line, but it's the same thing.
Yeah, it's the center path. Okay, good. So there are no further questions. We are a little bit above the beyond. Yes, John is saying sub-routinization is using bits of shapes, and Rafael knows the script from Toshi, and yeah, good. Okay, excellent. Simon, this was spectacular. Thank you so much.
Very much. Thank you for inviting
Also,
me.
I think this is a good opportunity. I've just checked with John. He's agreed that we announce it now. So the next event that I was just telling you that we should do, yeah, we should do. So basically, this is not related to Simon's talk, but I was just chatting with him before. So this conference came up as an idea in the previous conference about business, and now we have another idea that I think we should be doing, which is a fundraising event for type tools. Because one, there's a massive need for connecting people who create type tools with their audience, and with fundraising to help them get started, help to support them, and also connect them with the feedback as to the types of things that people need in real life. So if we bring independent foundries who on their own are not able to commission tools, and then on the other hand, we have the amazing people, some of whom we are hearing from at this conference. And then we just put them together, come up with ideas, find ways to make things happen so that all this amazing technology that we are seeing, for the good, for the bad, we do it consciously, ethically, but basically we connect these amazing people with the community that needs their support, so that the latest technology is not there only to benefit those very big players who are able to commission it, but in order to support independent founders of all levels. So that's going to be the next thing we're going to be doing. Wait for us. We will announce it at some point. But in the meantime, thank you again for Simon. Thank you for everyone who is here with us today as well. But Simon, really spectacular talk. Thank you so much. This day could not have started better. So thank you again. And he's gone. Okay. Okay, good. So let's take a 2-minute break and then we come back for the next talk. Thank you.